we can calculate the pH in the buffer region using the Henderson-Hasselbalch expression. That says the pH is equal to the pKa plus the log base 10 of the ratio weak base to weak acid form. So here I've expanded the buffer region, and we know that at half equivalence, halfway to the equivalence point, the concentrations of the acid and base form are equal. So this ratio is 1, the log term is 0, and the pH is numerically equal to the pKa at half equivalence. Now, if the acid form is slightly higher concentration than the base form, this ratio less than 1, the acid form predominates. That's in this region where the pH would be less than the pKa. This term would be negative. And of course, if the base form predominates, you'd expect this term to be positive, and that occurs when the pH is slightly larger than the pKa. So the Henderson-Hasselbalch expression allows us to calculate the pH throughout this region. Now we define the buffer region, the region where this expression holds, to be from pKa minus 1 up to pKa plus 1. So, for instance, if your weak acid was acetic acid, it has a pKa of around 4.75. The buffer region would be from 3.75 to 5.75, 1 unit around the pKa. So let's look at that in more detail. Here's our Henderson-Hasselbalch expression. When this ratio HA A minus is 10, so there's 10 times as much base form than acid form, then the log term is 1, plus 1. You're at pHs of 1 greater than the pKa. And of course, if the acid form predominates, so you have 10 times as much acid as base, then that log term is minus 1. And you're in the region where the pH is pKa minus 1. It's interesting to note for these buffers, when you dilute them, the ratio A minus over HA doesn't change. If both are diluted by a factor of 10, the ratio is the same. So there's no change in pH for dilution of a buffer. So a buffer resists change in pH from adding acid, from adding base, and from dilution.